So where do we start? Let's start with our RUBP. Okay, we're going to do, remember, 3 of those. And they each have 5 carbons. Okay. They bond to carbon dioxide molecules from the air. Again, you're writing this as I do this. Then we're going to do 3 carbon dioxide, so our numbers work out in the end, and they each have 1 carbon. The enzyme that makes this happen is called rubisco. So we'll just draw that in there. Here's our little rubisco enzyme. All right, on the next step, because we've joined our 5 carbon plus our 1 carbon, we now have a 6 carbon molecule. And that one I don't care about if you know the name of it. But we now have 3 of them. So we have 3 6 carbon molecules, which then, remember, is very unstable, so it breaks apart into 6 3 carbon molecules. All right, so if you take them, you multiply them, right? 3 times 6, 18 carbons. 6 times 3, 18 carbons. We're just rearranging the carbons into different molecules. Okay, and then remember we're going to add some phosphates, and we're going to add some hydrogens, and eventually get to G3P. We're going to do that all in one step for your purposes. So, next step is to make our G3P. Remember, there's 6 total G3Ps. So 6. Oop, I want to do that in a thinner line. 6 G3Ps. And they, remember, are 3 carbon molecules. And how did we get to those 6 G3Ps? Had to take 6 ATPs and change them into ADPs. And we had to take 6 NADPHs and change those into 6 NADPs. Okay? Remember, we use the phosphate from the ATP, we use the hydrogen from the ADP that helped us to make our G3P. One of those G3Ps, better move my pen back up here now. One of those G3Ps can be used, let's do a yellow. To make carbohydrates like glucose. So 1 G3P can go to make stuff. The other 5 G3P are going to be recycled. Let's draw those in there. And remember, each G3P still has 3 carbons. All right. So we have 6 G3P, take away 1, we're left over with 5. Those 5 G3Ps, remember, get rearranged to make 3 RUBPs, because 3 carbons times 5 carbons, or 5 molecules, is the same as 5 carbons times 3 molecules. But in order to do that rearranging, we need to use some energy again. Need to use some ATP, So right here, this arrow, I would suggest you probably have more room, so maybe writing it over here on this side. I'm just going to squeeze it in down here. We're going to change 3 ATPs into 3 ADPs. Okay, again, so this actually happens right here when we're converting our G3Ps into RUBP. We need ATP again. So in total, we need 6 plus 3, or 9 ATPs, and 6 NADPHs to make the Calvin cycle work. Again, it takes a total, though, of 3 carbons in the carbon dioxide molecules to make 1 G3P at the end. Okay, so remember our numbers. Those are important in the Calvin cycle. All right, so that's all I'm going to talk about the Calvin cycle for now, but I do want to point out one more thing that goes back to the light reactions. The light reactions, remember, made the ATP and the NADPH that we're using in this Calvin cycle. But you'll notice, as I said, there are 9 ATP used and 6 NADPH used. So we actually need more ATP than NADPH for the Calvin cycle to work. So the light reactions have a little trick that they can do to make more ATP when it's needed. Okay, because the balance of the ATP and the NADPH is off. So every once in a while they have to make a little more ATP to keep the Calvin cycle running efficiently. So let's look at what they do. This diagram hopefully looks familiar from when you studied the light reactions. Okay, here we have photosystem 2. We energized our electron, we split water, passed the electron down the transport chain and made some ATP. Here's photosystem 1, where that electron ends up, gets boosted again, gets passed down the electron transport chain to make NADPH. So that should all look familiar. Those are our light reactions that we talked about already. What can happen to make more ATP, remember this is the whole reason we're talking about this, is we need more ATP made, because there's 9 ATP needed in the Calvin cycle versus 6 NADPH. What we do to make more ATP in the light reactions is to go through what's called non-cyclic electron flow. Flow. All right. Basically what that means is photosystem 1, remember that's right here, instead of using the electron that gets boosted right here and passing along the electron transport chain to make NADPH, that electron is used for something else. So you'll notice that all this stuff here is kind of shaded in gray in the background, and this stuff as well is shaded in gray in the background. That's to show that that's not happening. Okay? Instead, when we need more ATP for the Calvin cycle, the electron that comes from photosystem 2 still travels down the electron transport chain, resupplies the chlorophyll, the light bumps that electron up to a higher energy level, but it goes to a different electron acceptor, which feeds it back into this electron transport chain that makes ATP. So instead of using the electrons to make NADPH, it recycles them through this original electron transport chain to continue making ATP. So non-cyclic electron transport flow, or electron transport, or electron flow, its whole purpose is to make more ATP again for the Calvin cycle so it doesn't run out, and it only requires photosystem 1 to be charged up. As long as photosystem 1 is getting light energy, it's going to continue boosting that electron through the original electron transport chain and making ATP. Once it's caught up and it's got enough ATP, then both photosystems will come back online and it'll start making NADPH again, along with the ATP it usually makes. So the chloroplast can sense when it's getting low on ATP and it needs to shift to this cyclic electron flow. Oh, I called it non-cyclic, didn't I? Sorry. This is cyclic, so erase that in your notebook because it's a cycle, right? Just like the Calvin cycle or citric acid cycle. So this is cyclic electron flow when it needs to make more ATP. It's called non-cyclic when it's going through the regular reactions of photosystem 2, photosystem 1, making ATP and NADPH. Alright, so to make that more clear, since I made a mistake, I want to make sure to clear that up. Non-cyclic makes ATP and NADPH. So it requires both photosystems. Cyclic makes only ATP. And again, the reason goes back to the fact that the Calvin cycle needs 9 ATP for every 6 NADPH. And so at some point it's got to catch up and provide those extra ATP for the Calvin cycle.